We have two main goals for this lecture. The first is to motivate, define, and see how to compute the variance. Okay? And what's the variance? It's a measure of the expected deviation from the mean, okay, where the mean is the expected value of your random variable. So it's a measure of the expected deviation from the mean when you actually run the experiment. When you run the experiment, the actual outcome may deviate from the mean. Okay, and how much do we expect it to deviate? Okay. And then we're going to use the variance to describe what are the likely outcomes when you actually run the experiment. So what are the likely outcomes of the random variable? So let's start with the variance. So the variance. Okay, so it's a measure of the expected deviation from the mean. So from now on, we're going to call the expected value of a random variable the mean, okay? Because otherwise we have too many expecteds flying around, so it's a little bit more convenient. Okay, so let's consider an experiment. Roll 2 dice and take the sum. Okay, so sum of 2 dice. Okay, and what are the possible outcomes? So the random variable is the sum. What are the possible outcomes? So we know the possible outcomes. The possible outcomes are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And what are the probabilities? So the probability P sub x of little x, so the outcome little x. Okay, 1 over 36, 2 over 36, 3 over 36, 4 over 36, 5 over 36, 6 over 36, 5 over 36, 4 over 36, 3 over 36, 2 over 36, 1 over 36. Okay, so those are the probabilities. Okay. And we computed the expected value. So the expected value, and we typically use, so you have a random variable x, okay, its expected value is expected value of x, and we often refer to this as mu for mean, mu for m, mean. Okay. And so we computed the mean mu is equal to, you weight 2 times this probability plus 3 times this probability and so on. Okay, so the expected value is 2 times 1 over 36 plus 3 times 2 over 36 plus and so on plus 12 times 1 over 36, and this was equal to 7. Okay, so mu equals 7. Okay, now if you run this experiment, okay, you will observe either 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. You may not necessarily observe the mean of 7. Okay, so so we can define the deviation, okay, delta, which is the deviation from the mean. Okay, so this is, when you run the experiment, you measure a random variable value x, okay, and you subtract from it the mean, x minus the mean, mu. Okay, so this is the deviation, okay, the difference between the observed value and the mean. Now, by the way, the mean is a constant, it's just some number. Okay, it's not going to change each time you run the experiment. What changes each time you run the experiment is the random variable x. Okay, but when you run it, we can see how far did you deviate from the mean. So what are the, for each possible outcome, there's a possible deviation. So let me list the deviation. So if the actual value, the observed value is 2, the deviation is minus 5. 3, minus 4, minus 3, minus 2, minus 1, no deviation. Okay, if the actual observed value is 7. Okay, now we have a deviation of 1, 2, 3, 4, 5. So there are possible deviations. Okay, and so pop quiz. Pop quiz. Okay, so first I want to emphasize that the deviation is another example of a random variable, because look, it takes on possible values. Okay, and each of these possible values comes with a probability. Now, it turns out that this deviation is very closely related to the actual observed random variable x, the measurement we're interested in. You just take the measurement and subtract the mean. So this deviation is a function of the random variable x. Okay, we've seen functions of a random variable before. Okay, so the deviation delta is a random variable. Okay, it is a random variable. Okay, and so we can take the expected value of the deviation. So the pop quiz for these deviations, what is the expected value of the deviation? Okay, so we'll give you 5 seconds. Compute the expected value of the deviation. Pause the video. 1, 2, 3, 4, 5. Okay, so unpause if you're coming back and you just are here for the ride. Okay, great. if you figured out that the deviation has an expected value which is 0, okay, fantastic. And you could have done that by just seeing that, this 5 and that 5 will, you multiply this guy by its probability, okay, you get minus 5 times 1 over 36, 5 times 1 over 36, they cancel. Then the 4's cancel with the minus 4. 3 and minus 3 cancel. 2 and minus 2 cancel, 1 and minus 1 cancels, and this is a deviation of 0. Okay. In fact, it is generally the case that when you take the deviations from the mean of a random variable, the expected value is 0. Why? Because we're taking the expected value of x minus mu, and the expected value of a sum is a sum of expected values. This is the expected value of x minus the expected value of mu. Okay. And the expected value of x is by definition mu. Okay, and this is just a constant. It's a constant. So the expected value of a constant is just a constant itself. Okay, so mu minus mu equals 0, always. So the expected value of deviations is always 0. So the deviations themselves, if you take the expected value, is always 0. It doesn't quantify how likely it is that you will observe something that deviates from the mean. And that's because when we typically talk about deviates from the mean, what are the deviations from the mean? We're only interested in the size. So, the fact that this is a minus 5 and the fact that that's a 5, they both have size 5. Okay, so it turns out that the size itself, okay, that's one way to get all positive deviations, but the size is inconvenient to work with. Okay? It's more convenient to work with the square. So let's look at the deviation squared. Okay, so this is 25, 16, 9, 4, 1, 0, 1, 4, 9, 16, 25. So those are the deviations squared. Okay, and so pop quiz. Pop quiz. Compute the expected value of the deviations squared. Okay, so pop quiz computed. So you just, what is it? Okay, so I'll pause the video 1, 2, 3, 4, 5, give you a chance to do it, and then I'll show you what it is. So the expected value of the deviations squared is, 1 over 36 times 25, 1 over 36 times 25 plus 2 over 36 times 16, 2 over 36 times 16 plus 3 over 36 times 9 plus, and so on, and so on, and so on. And the last term here will be plus 1 over 36 times 25. And that is exactly 5 and 5/6. So if you pause the video and got 5 and 5/6, fantastic! You know how to compute expected values, even of complicated random variables. Good. Okay. What you will observe is that the deviations are all positive. Okay, the deviations squared are all positive because we're squaring a real number. And so the expected value is you multiply positive probabilities with positive squares and then you add them up. So the expected deviation is always positive. So no surprise here. Okay, and it turns out that this expected squared deviation is this important quantity that we call the variance. Okay, so definition. The variance is equal to the expected value of the deviations squared. So for random variable x, for random variable x, and the deviation delta is equal to x minus its mean, which is equal to x minus its expected value. Okay, so that's the definition of the variance. Okay. But you will observe that the variance, in some sense, has the dimension of the deviation squared. So it's a square of a deviation. So if we want to measure the deviations, then we should take the square root. Okay? And so the square root of the variance, okay, is also an important quantity. So definition. The standard deviation is equal to the square root of the variance, which is the square root of the expected value of the deviation squared, which is the square root of the expected value of the random variable x minus its mean squared. Okay, so this here is the expected value of x minus its mean squared. That's the variance. Okay, so two important definitions. Okay, and if we take the square root of this guy, then the standard deviation. So the standard deviation, now we typically give the symbol sigma for S, sigma to the standard deviation. And so sigma is the square root of the variance. So the variance is, we typically call sigma squared. Okay. So for the sum of two dice, so for the sum of 2 dice. The variance sigma squared is equal to 5 and 5/6. And the standard deviation is the square root of that. Square root of 5 and 5/6, which is equal to approximately 2.52. Okay. And sometimes you'll hear people say, that the sum of 2 dice, or the sum of 2 dice is 7. It's mean, so this is the mean, mu, plus or minus 2.52. This is the standard deviation. Now we'll see later in this class, in what sense this is true. So you can think about it as identifying a range. 7 plus or minus 2.52. Okay, when you roll a pair of dice, that's the likely outcome, somewhere in this range, which is approximately 4.5 to 9.5 when you roll the sum of 2 dice. Okay. All right. Okay. Let's take another example. And, very often, probability is used in analyzing gambling games. Okay, so let's take an example of a gambling game, and that'll show you one of the other interpretations of the variance, which is as risk. So, variance, or more specifically, standard deviation, is a measure of risk. Okay, so now I'm going to show you 2 gambling games. Okay, so the first gambling game is as follows. It's defined by a random variable x1. Okay, and x1 is the following random variable. Either you will win $2, okay, with probability 2/3, or you will lose $1, your minus $1, with probability 1/3. Okay, and I'm going to show you. So, do you want to play this gambling game? Yes or no? We're going to try to analyze that probabilistically. And there's a second gambling game. Okay, also characterized by a random variable. In this case, x2. Okay, and in the second gambling game, you can either win $102. You can either win $102 with probability 2/3, or you can lose 201. So you can lose $201 with probability 1/3. Okay. So many things are similar about these 2 gambling games. For example, the probability to win in each case is 2/3. The probability to lose in each case is 1/3. Now, it is true, okay, that the amount you win or lose here is much smaller than the amount you win or lose there. Okay. But since the outcome is random in each game, let's compute the expected value. So the expected value of x1. So what's your expected profit? Is 2/3 times 2. Is 2/3 times 2 plus 1/3 times minus 1, which is equal to 1. So you expect to make a profit of $1. So you might think, yes, I would certainly be interested in this gamble. Okay, so you expect to make a profit of $1. What about this gamble? The expected value of x2. Okay. What is it? Well, it's 2/3 times 102. 2/3 times 102 minus 1/3 times 201. So 2/3 times 102 is divided by 3, you get 204. Okay, minus 201, which is 3/3. So this is also equal to $1. These gambles are getting more and more similar. Okay, so you see, in this gamble, if you take this gamble on, you expect to gain $1. And if you take that gamble on, you expect to gain $1. But now, if in the live class, when I ask students, and I ask them to answer honestly, would you take this gamble on? Many of them would say yes. Would you take this gamble on? Many of them would say no, and I would also say no. Okay, and why? Okay, and why we would take this gamble on but not that gamble on is because here, think about the situation where you lose $1. Okay, and think about the situation where you win, you win $2, and on average, if you play this game many times, then you should take this gamble on, and you will gain $1. But if you're asked to take it on once, okay, your expected winnings is $1, but you could lose $1, and okay, that seems like a reasonable trade-off. I could lose $1, but on average, I'm expecting to win $1. Okay, and sometimes, on the times where I win, I will win $2. Okay, but now here, my expected winnings is still $1, but now if I lose, I'm down big time. I'm down $200. And if I win, I'm up $102. Okay, And it's a very risky game, this one. Okay? But nevertheless, the expected values are the same, and the difference between these two games becomes, more evident when we look at the variance. So the variance of x1. So now we know the mean. So the variance of x1 is 2/3. So we take the deviation. So this deviation is 2 minus 1. 2/3 times 2 minus 1 squared plus 1/3. 1/3 times minus 1 squared. And so the variance of x1 is equal to 2. Okay. Because here you get 2/3 plus 1/3 times 4. Okay, which is 4/3. So the variance is 2. Here, the variance of x2 is equal to 2/3 times 102 minus 1, 102 minus 1, so the deviation squared, plus 1/3 times minus 201 minus 1, so minus 201 minus 1 squared. And this is a big number. So the variance here is approximately equal to 2 times 10 to the 4, so 20,000. Okay, so the standard deviation here is square root of 2, and so we would say that if you take this gamble on, you expect to win 1 plus or minus 1.44. Okay? You expect to win 1 plus or minus 1.41. Okay? And if you take this gamble on, so the standard deviation sigma is square root of 2 times 10 to the 4. So you expect to win 1. Again, you expect to win 1, but now it's plus or minus the square root of 2 times 10 to the 4, which is 141. Okay. And so you see, here, the gamble is you can win 1 plus or minus 1.41, so it's not that risky. Here you'll win on average, you'll win 1 plus or minus 141. Well, actually, you'll either win 102 or lose 201. But, the variance is sort of capturing that. Okay. The variance and the standard deviation are much larger in this second gamble than in this first gamble, and that's capturing this notion of risk, even though the expected values are the same. Okay. So variance can capture this, everyday phenomenon of which we like to stay away from, which we call risk. Okay. Risk somehow is, typically we measure risk as downside, but variance captures risk in the sense of variability. Okay. So let's erase and come back and talk about computing the variance.